right, welcome back everybody. We'll continue with Mateusz's talk.
Okay, thank you very much. Thank you for coming back after lunch instead of taking a nap. I mean, you can take a nap in the room if you don't snore, right? So so I wanted to leave this for a while so that you remember this example where I basically say that this antipode S somehow doesn't work really that nice. Right? And then now I'm erasing it, and so basically now
There's a question.
Yes.
Why this antipode doesn't work?
Yeah, so there was like if you compute the antipode on like this gamma or gamma star, you get eigenvalue which is bigger than 1. It is like 1 over q, and then if you multiply them, it explodes. Yeah, that's the issue. Yeah. Okay, so then the conclusion basically was that so now everything will be just compact, not locally compact, just compact. So if G was like a nice compact group, then we can encode its structure using the algebra of continuous functions on G. Right, and then on this, we can define these maps, the delta, the S, the epsilon, and it recovers like all the structure of the group. But this example of SEQ2 was basically to show you that somehow delta is okay, S is probably not okay, epsilon we don't know yet, but it turns out to be like not exactly okay as either. So, but there is some hope, because if you're a classical group, right? Multiplication is the only thing you need. Like if you know it's a group and you know it's multiplication, then the inverse and the unit are uniquely determined. So there is a hope that maybe you can define compact quantum groups just using the multiplication, satisfying some extra axioms that tell you that you don't have just a semigroup but an actual group, right? So that's inverses exist actually, and that's exactly what Wasilewski did. So this will be the definition. So a pair A delta, okay, where A is a C-star algebra. So I think in the original definition of Wasilewski, he assumed that A is separable. I guess it's fine for us. We'll not need not non-separable, but also you don't have to assume it, so I will not write it down. And delta. Yes, thank you. Somehow for me everything is unital, because I'm mostly a phenomenological person, so somehow unital is just is unital. But yeah, that's true. It's a good point. It's unital C-star algebra and a star homomorphism. Star homomorphism. Delta from A to A, okay, which is co-associative. So satisfies this axiom for co-multiplications, co-associative. And this pair is called a compact quantum group. And then we have two weird conditions, like if span of the elements of the form A tensor 1 delta of B, where A and B are in A, is dense in A tensor A. And we have a symmetric version of that. So is span of the 1 tensor A delta of B Okay, so why do we have this weird definition, right? I mean, maybe it's very nice, but what does it have to do with being a group? So basically, if you look at this thing, so it's like spanned, and say in the classical case, right? So A is just continuous functions on an actual compact group. Then this is spanned by functions of the form F1 of G times F2 of GH. Okay, and then these conditions are typically called cancellation rules. Because like if you have, so imagine that GH is equal to GK. It might happen in a semi-group, right? In a group, I mean, unless, yeah, and H is not K. And then, so then F1 of G, F2 of GK is always equal to F1 of G, F2 of GH. Right, but then by assumption, the span of these functions is dense. So it follows that any function in C on the product of G with G is also equal on these pairs GK and GH. So it follows that F of GK is equal to F of GH for each continuous F on the product of G with itself. But then these functions, I mean, the continuous functions, they separate points. So it means that from this it will follow that H is actually equal to K. And then the other condition, the opposite one, is for the cancellation from the other side. Basically, this is equivalent to this cancellation rule. And then there is this statement, I don't know, let's call it proposition or theorem or something, that any compact semigroup, so still classical thing, satisfying these cancellation rules with cancellation is a group. So this will be, I think, a nice thing to discuss during the tutorials on Wednesday, is this classical statement. But then this shows you that if you assume that A is a commutative C-star algebra, so it's functions on some set, then this delta gives you multiplication of the set, and the cancellation rules tell you, using this proposition, that you actually get a group. So if you restrict to the commutative case, this is actually a definition of a compact group. So that's why Waterloo somehow generalize it, to compact quantum groups is when you lose the commutativity of A. These are the compact quantum groups. And then, I will soon go into a list of examples. But first, I want to define a subclass of these compact quantum groups. Definition. Okay, so A delta is called a matrix compact quantum group. If it is generated by elements, so basically the matrix entries, so by elements uij, such that the co-multiplication is given by this matrix multiplication, so some, it's like, uij, ij go from 1 to n, so it's a finite matrix. Delta of ij is a sum over k from 1 to n, uik tensor ukj. Okay, the matrix, So U, the matrix with entries Uij, it's a n by n matrix with entries in A. It's unitary. And this is something that is somehow automatic classically, but not really automatic here, is that this U, I wanted UC, right, Mike? So this UC, which is the same matrix, but with Uij stars. So basically, like classically, it would be like the complex conjugate of the unitary matrix, so still unitary. We want something weaker, so we want this to be this invertible. This other extra condition is unfortunately not automatic. Yeah, and then so you can and when you see the proof of this, which I will not show, is that basically you use this condition to obtain this cancellation rules. So to have this density of these specific subspaces. And I wanted to give this definition because the examples that I will give are of this form. Yes.
It's not enough that U is unitary such that UC is invertible.
Sorry?
So you have examples where U is unitary, but UC is.
Yeah, I think there are examples. I don't know when I can put this particular example at the top of my head, but there are examples. Yeah. Don't remember. Okay, so.
And hereby generated, you mean C star?
Sorry?
No, but then you see is invertible.
Yeah, it's invertible, right? Yeah, because it can be non-unitary. That's easy, but non-invertible, it's a bit more. Yeah, sorry, I didn't get the question.
So hereby generated, you mean that the C star algebra A is generated by these?
Yes, I mean that there's like these are like a bunch of operators. You take a look at star algebra generated by it, and then take the closure, the norm closure of it inside some ambient Hilbert space, which is not to be revealed. I mean, there is some abstract Hilbert space we don't know and often don't really care what it is precisely. Okay, so I have a list of examples. Yeah, maybe I should say that one often writes that A is C of G, where G is a compact quantum matrix, compact quantum group. So if you have good imagination or you're delusional, you can believe that there's an object G, like boldface G, which this A is a space of continuous functions. So that's I wanted to say because I will rewrite, not always write C of something, but I will write these objects. So the first example is the one I already introduced. So this is this SUQ2. Right, so recall that the parameters were real, 0. What's the second one? So the second one will be like the analog of the unitary group. So you have what we call the free unitary group. So UN plus.
Mateusz?
Yes.
So what happens if you take like maybe Q was a formal parameter or Q on the side of that domain? Like what happens? What phase?
I actually. So there are versions like.
So first of all, if
You're in the real line.
the real line doesn't matter.
It's like 1 over you just take 1 over Q and it's like the same.
Okay.
So then when you're and then like there are these versions when on the unit circle, for example.
And then it becomes tricky.
So there are things that can happen, but it's not that clear. Yeah.
So it's not a compact matrix quantum group.
No, I don't think so. No. You have a question?
Maybe just a
Comment.
I think when you use complex, the star structure becomes
Yeah. Yeah, that's true. Mm-hmm. Right. So this is probably to have more algebraic approaches. Yes.
But actually, the Q complex is very important for physics.
Yeah, but it's somehow more difficult for. Yeah, it's like. Yeah, I agree. Like sort of like on the unit circle, things like that, or like roots of unity and things. Okay, so UN plus. So classical UN group is just the group of unitary n by n matrices. So here, this is. So C of UN plus is generated by Uij's such that, and what we assume is that, well, the matrix U, so this operator valued matrix, is unitary. And this matrix of complex conjugates, so Uij star, is also unitary. It's generated like there is some sort of universal construction of an algebra, of a C algebra generated by objects satisfying this kind of relations. And then, yeah, so as always, you would write the co-multiplication is always the same. So it's the delta of Uij, sum Uik, tensor Ukj. And then to have such a star homomorphism, you have to show that these elements, which are to be images of Uij's, satisfy the relations satisfied by Uij. This is something we can do, and maybe in one of these examples that in the tutorials we can actually do the computation. So 3, this is the analog of the orthogonal group. So it's called On plus. And then, yeah, C of On plus is generated by Uij's such that U is equal to UC is unitary. Right, so this is somehow the real version of that. We assume that, yeah, the entries are self-adjoint, so this is like a real version of that. I don't want to erase that, I want to keep that. Yeah, actually maybe I should add the cancellation rules. To the list of things to remember. So like C of G tensor 1 delta closure is C of G tensor C of G is equal to the other. Okay, and then, yes. I mean, no, it follows from the invertibility of the UC, right? Yeah. Yeah, we don't add anything extra. That's why it's somehow potentially easier to check. So then, yeah, example number 4. So these are, yeah, we have analogs of some classical Lie groups, right? Of unitary groups, of orthogonal groups, of these special unitary groups. What are like other nice examples of groups that we know? The first thing you see in a group theory course is probably a permutation group, because you know that any finite group embeds in a permutation group, so permutation groups are important, and we have analogs of these as well. Then it's Sn plus. So what was it? So yeah, it's generated by, this time I'll use different letters, so elements Pij, such that P is unitary and each Pij is a projection, right? Just like Robin defined like an orthogonal projection, so Pij squared is Pij, it's Pij star. So why is it an analog of, or like a generalization of the classical permutation group? So if you think of classical permutation groups, so you have a permutation matrices. So of course all the entries are either 0 or 1, right? So this is precisely this condition, and then this condition for matrix of projections means that each row and column sums up to 1. So each row and column sums up to the identity operator. So it means that if you have only 0 and 1s, it means that in each row and column you have exactly 1, 1, and everything other is 0, which is exactly a permutation matrix. So that is why this is an analog of the permutation group. But then there is this funny thing that, okay, classical permutation, these are all like nice continuous Lie groups, infinite. Permutation groups are finite, but for some reason in quantum group theory, permutation groups are often infinite. So for n equal 1, 2, 3, we have Sn plus is equal to Sn. So what I mean by this is that the C-star algebra generated by the PIJs is commutative, and it's actually isomorphic to the C-star algebra of functions on Sn. But for n at least 4, this C of Sn plus is actually infinite dimensional. So it's an actual, like, genuine infinite compact quantum group. It's not really finite anymore. And how do you get that? I mean, as always, I mean, you're supposed to construct some representation so that you know that these things exist. And an example of such a P is to take P, say n is 4. Take P to be equal the following thing. So we take projection P here, 1 minus P here, 1 minus P here, P here. Have zeros at the off-diagonal blocks. And here you have some different projection Q in the other 2 by 2 block. Okay, so for some projections and there is no relation between the P and Q, so you can choose them freely. So you get some sort of free product as a quotient of your history algebra. So it's definitely infinite dimensional. How you get some representation in which this thing is infinite dimensional. But as you see, somehow you need really 4 to have this construction where they are somehow completely unrelated. So for n equal 1 and 2, it's very easy to show this. And for n equal to 3, I mean, there's still a computation, but you need to work a little bit. And then, before I continue, other examples, maybe I want to, maybe I will skip it then. Yeah, because we'll probably mention that at some point, but there are other versions of these UN pluses and ON pluses, somehow slightly even more general, but I think I will keep it for later. Because somehow this last example, and like all examples that you see, somehow, how do you see groups classically? I mean, they are symmetries of some object, right? Like SU2, I mean, sort of like volume or orientation preserving automorphisms of C2, things like that. ON plus is the same. Sn, these are just self-bijections of a finite set. So basically, what groups are supposed to do is to act on sets, right? Act as symmetries of some objects. So this is the notion that I want to introduce now. So actions of of groups. But one final comment. Yeah, maybe even without writing it down. Maybe I will write it down. So there is a theorem. So because during my first lecture there was a question, why do I assume locally compact, right? It was a good question, and the answer was that basically the only realm in which you can do this sort of analysis because you have a Haar measure. And then there's an analog of a Haar measure for compact quantum groups, and it's somehow the setting is robust enough that you can always prove that there exists a Haar measure. So what it means, so I'm stating the theorem, so on every compact quantum group there exists an analog of the Haar measure. So of course, as always, I need a name, so it would be G. Which what it is? It's a state. So I will define a state on C of G. State H on C of G. Which is invariant. Okay, so there are some words that I have to define. So first of all, I need to draw here. So first of all, state. It's a linear functional. Such that h of x is non-negative if x is a non-negative operator, right? We're in system algebras, they are always inside some b of h, so we know what it means for an operator to be positive. Right? It means that all its all linear products like x, v, v are non-negative. So as state this plus is normalized. So when h on the unit is equal to 1. So this is exactly an analog of a probability measure. Right? It's a thing that takes a function, spits out a number, take a positive function, the number is positive, and on 1, so on a constant function it gives 1, so it's normalized. And invariant so this is invariant for the multiplication, and it means that H tensor identity delta x is equal h of x times the unit, and also the opposite way. Okay, so what it means is that so it means that it's both right and left invariant, just like for classical compact groups. Yeah, this is for any x in C of G. So it means that you can do analysis on these compact quantum groups, right? You can define the L2 space, you can define the L infinity space. If you work a bit harder, you can also define LP spaces, and you can do reasonable analysis. You can also define Fourier transform that we will do in a couple of lectures. So they're like not only super abstract objects, but they also somehow are analytic objects.
So if you just have locally compact, will you have two different, one right and one left?
Yes, in general, yes. Yes, and there is, yeah. But we will not really go into locally compact quantum groups in this lecture series. But yeah, that's true. Just like for classical groups, but there are even more surprising things for compact quantum groups. That, for example, you can have a discrete quantum group which also has two different Haar measures, which classically, of course, it's not possible. Okay, so actions of compact quantum groups. so first we have to identify what is the class of objects that we want to act on. So classically, you want to act on spaces. Say for simplicity, we'll stick to compact case. So actions of compact groups on quantum spaces. On compact spaces. Actually, compact quantum spaces, but yeah, everything will be compact. So as we already discussed, somehow an analog of a compact space is a unital system algebra. So what we need is a unital system algebra as our space, some compact quantum group, and something that will be an analog of the action. So so an action of a compact quantum group G on a unital system algebra. I mean, you can do non-unital as well, but it's slightly more technical. A is once again a star homomorphism. Alpha, which goes from A to A tensor C of G, such that I'm just trying to, in order not to try to figure it out by looking at it, I will just write out what I have here, such that alpha tensor identity composed with alpha is equal to identity tensor delta composed with alpha. So maybe try to make it clearer. So we have A going from A to C of G. Okay, so that's your alpha part. Then you have this. Okay, you can either act with alpha on this part and as identity on this part to create alpha tensor C of G tensor other copy of C of G. So you can do this alpha tensor identity into A tensor C of G tensor C of G. That's one way to create this sort of tensor product, and the other way is to apply delta on this part and identity here. So it's alpha, so it's identity tensor delta, tensor C of G. And we want these to be, these maps to be, equal. And this is really coming from the fact that if you have an action, classical action, so classical action, so this is a right action, so classical action. So it's a map from some space x times g to x, right? So by dualizing, we get this homomorphism, right? So from this, you get C of x into C of x tensor C of g. And this is basically associativity. This condition is associativity, just like the other one. Okay. So I will maybe add this as well. So actions.
Is alpha unital necessarily?
Not really. I think you need to do multiplier algebras if you're non-unital.
I think the question is alpha unital.
Alpha unital. Sorry. I guess we assume that. Yeah. Sorry, I thought you meant the other question.
I actually don't know what I said. I have a question.
So we answered both questions. Okay, so we have this notion, and it seems natural that, for example, this quantum permutation group, it should act on something. And it will act on the space of functions on n points, which is just Cn, right? example is that Sn plus acts on Cn. So how does it act? We define alpha from Cn tensor C of Sn plus, and we just say that alpha on its canonical basis vector EI is the sum over EJ. There's a convention you have to choose. I think PJI. Yes?
I guess you also want to put this density condition.
Yes, sorry, yes, that's true. Yes. That's true. This is like still, you can have a group which acts like a semi-group in a way. So you don't know if the unit acts as a unit, right? So yes, we want, yeah, sorry. Yeah. Forgot about that. Where do I have it? I have it there. Yeah, so there is an extra condition. So just like, yeah, this is roughly an analog of this cancellation rule. So like there's Polish condition.
I will check if it's really necessary.
Yeah, it is necessary. Yes. There, it is necessary. Yes. And the Polish condition is okay that alpha of A, so like the span of alpha of A times 1 times C of G should be dense in A tensor C of G. So if we have a co-unit, this epsilon, so if we have a co-unit, then you can write this condition as somehow unitality, so identity tensor epsilon composed with alpha is identity. Because somehow we don't need that much cancellation rules anymore because we know that you start from a group, but we need something in order to know that the unit acts really as a unit. Somehow, yeah. And this is this condition. Okay, so this is an example of an action, and in fact you can somehow Sn plus is the universal object among compact quantum groups acting on Cn. So this is somehow a general theme that you can have objects. Typically, it's easier if they're finite, or at least compact, or things like that. And then you can ask whether there's actually like a universal, like an automorphism group of quantum automorphism group of this object. And Sn plus is an example of that. Like you start from Cn, you look for the universal object. So basically, universal means. So what would be like a general action on Cn? Like if it is an automorphism group, the automorphism group of this, it means that any action of the other group will be just a homomorphism from this group to Sn plus, right? To the automorphism group of the object. So being universal means basically that any other action factors through this canonical action in some way. And you can prove that Sn plus is like that. But then you can imagine other objects on which you can act. Right? Even starting from Cn, so this is just endpoints, but you can look at structures of finite sets, right? For example, graphs. You can ask about quantum automorphism groups of graphs, and you can do that as well. So I want to keep Sn plus. And then, classically, if you have a graph with n vertices, its automorphism group will be a subgroup of Sn, right, of the permutation group. And somehow, in our dual setting, it means that the algebra C of the quantum automorphisms of some graph should be the quotient of C of Sn plus. And we can exactly identify by what we have to quotient, by which relation. So say G is DE finite graph. Maybe finite is redundant because I'm about to say that it's on n vertices. Then we can define odd plus of G would be the universal CQG compound group acting on Cn and preserving the adjacency matrix. So what does it mean? Preserving or commuting with adjacency matrix of G. So what does it mean? It means that we have an action Cn to this C-star algebra of quantum automorphisms of this graph. Sorry, tensor product. And we want that if we act with adjacency matrix of our graph on Cn, and then we do the action, we want it to be the same as alpha tensor identity when you do the so you do alpha first and then you act with A on this part. And we actually have that let's see on the automorphism, quantum automorphism group of a graph is isomorphic to C of Sn plus, and the quotient is by the relation that our P, so the matrix, the quantum permutation matrix P, has to commute with this adjacency matrix. Right, so we can write this as, I mean, this is a scalar matrix, it's an operator of values matrix, but you can imagine, you can just write the formula. And these are the relations that P has to satisfy. Extra conditions so that it can act on the graph. Okay, and then just like in Sn plus, I gave you an answer, right? For n1, 2, 3, this is just the classical Sn group. For n4 and bigger, it's much bigger. Then for general graphs, you can ask these questions, right? Whether this quantum automorphism group is actually something bigger than the classical automorphism group. And there are examples where, in a way, I already gave an example. Like, if you have just 4 points, the complete graph or the trivial graphs on 4 points, it's much bigger. But there are examples of graphs, for example, cycles are graphs which actually do not admit extra quantum symmetry. Like, I mean, unless n is 4, actually, I think n4 is special for cycles, but if 5 and bigger it's actually, they don't have quantum automorphism. So there are examples going one way and the other. And there's also, I have -7 seconds, so I think we just say one final sentence, that is, there is a relation to quantum information. There are these non-local games where you have 2 graphs and you ask whether they are isomorphic, and there is a classical game which you can win if and only if the graphs are isomorphic, and then there's a quantum version which leads to the definition of a quantum isomorphism of graphs. And somehow this notion from quantum information somehow translates to a very similar statement, so that there is a sort of this permutation matrix that intertwines the adjacency matrices of the respective graphs. And it might happen that you have 2 non-isomorphic graphs that are quantum isomorphic. Okay, thank you very much.
Thanks a lot. Are there any questions?
So for instance, for permutation groups, I guess you can like go from the abelian classical group to the thing you just defined, but are there like intermediate permutation groups where you get like
manifolds, star algebras, or anything of that sort, and that's still meaningful as a.
I mean, there are sometimes things in between, right? This is, but what do you mean? Like, what are the amenable C algebras that you want to have?
So how large are these like C and plus? Are these like generally non-amenable? Like I don't know if it's
Possible to mild it down.
Actually, are they nuclear? The C of S and plus, these are. They're not because they contain the quotient onto these free products.
For n greater than 4.
Or n greater than 4, they quotient onto these free products, so they are not. So we wanted something amenable inside between.
Yeah, but it's still a permutation in some sense.
I don't know.
I mean, there's this maximality conjecture
Right.
asking, is there a compact quantum group sitting between Sn and Sn plus?
Yeah.
But that's an open problem.
That's another problem. Yeah. I mean, it's only in some
Anything,
small
and
cases.
It's not even asking for amenable. Just
Yeah,
asking whether
it's not
any
clear.
quantum group between them.
Yeah.
Okay, thanks.
Yes.
The example you gave about the permutation group, it looks like this. This was like a trivial example because there are lots of zeros. Is there some notion that it looks like reducible? Is there a notion of irreducibility for these representations that you were talking about?
I mean, there is in general a notion of irreducibility of representations of these compact quantum groups, just like for classical groups. It's like almost, we'll get to that. But the examples, I only gave examples showing that it was a particular representation somehow that was reducible, right? But somehow the universal one, in a way, isn't. Like, I mean, somehow you can get representations in which you don't have these zeros. That's what I mean. It's not really irreducibility of the representation. Yes?
Your condition of universality so means that anything else, for example, that acts on C to the n maps to this C star, so to C of Sn plus?
I mean, so it's on the level of the groups would be into Sn plus, so on the level of algebras it's like here. So anything is a quotient of anything acting on Cn will be a quotient, the algebra will be the quotient of C of Sn plus.
Do you have some uniqueness of the homomorphism as well?
Yeah, I think so. Yeah, this is part of the universe. Yeah, somehow, yeah.
And for the thing with the graphs, the classical symmetries are part of this.
Yes. Yeah, it's always somehow bigger. I mean, it's always not smaller. Yeah. Because somehow you always recover the classical automorphism groups as somehow you take the Abelianization of the system algebra, and then you get the commutative system algebra, which is the functions on the classical automorphism group. Yeah, Roberto first and Ivan.
So is there any moral reason, I guess, back to the quantum permutations of cycles for being the exception?
I mean, yeah, in general, it's like, so cycle is basically a cyclic group, so that you can compute easily the composition of the quantum ideal matrix, like a spectral composition, and you get plenty of intertwiners in a way, which somehow allows you to reduce things, roughly. That's, roughly the idea, I think. And Ivan?
Is there any formal way to reach, let's say, SUQ converges to classical SU SQ tends to 1?
I think there are ways, of this convergence, But that's probably in terms of like this maybe compact quantum metric spaces and things like that. Like you can have this, there are compact quantum metric spaces in the sense of Riefel, and there's this Gromov-Hausdorff convergence, things like that.
You can also think about the continuous field of sister algebras.
Oh yeah.
Because it's not a trivial result, but it's known that they form a continuous field of sister algebras. So essentially you put them into a huge sister algebra, and there is a kind of in some way there.
Any other questions? Anybody? Okay, so this thing which you did.